Okay, so now we're going to consider, lenses. And when we did our, focusing mirrors, the spherical mirrors, last week, usually when you think of focusing of light in imaging and stuff like that, you think of lenses, right? Lenses transmit light. So how do they work, right? Well, using this idea of the time of this principle of least time, right? If we're going to arrive at some point, right, we need to consider optical paths. I guess I should have written this here. That have exactly the same. So if we, start from here, we're looking for some way to make this happen. Okay. All right. So this marks a point in time. Okay. And so this ray, as it travels from here to here, this path will be the same length as these paths here, right? And so how do you do that, right? That's the question. And if we introduce a material, right? So if we introduce a material whose index of refraction is greater than, say, air, which we're assuming this is what our rays are in, then it will introduce a delay in the arrival time of these waves, right? So let me just, before I draw this, let me draw the following. If I've got these three rays, and then I put a big, thick piece of glass in here, and this is coming in at normal incidence, right? And I'm going to use a term, let's call it a wave front, even though we haven't talked about waves. We'll call it the light front, right? So here we were at t equals 0, right? These three rays all depart at the same t equals 0, right? And then at some later time, t equals, well, just some later time t, right? We might find these two rays here, since they have basically traveled in the same direction in the same material, they're traveling at the same speed, so they'll have traveled the same distance, right? It's, the speed of light times this t will give us this distance here. But this ray didn't go as far, you see?
Yes.
And why didn't it go as far? Well, because it traveled through this material here, which we said was glass or something, right? Which has some, N2, which is greater than 1. So its index is larger than 1, which means that this ray gets delayed in its arrival. So they're kind of separated, right?
Yeah.
So we can imagine, right, using this principle of least time, finding a clever way to design a piece of glass, right, to make these travel times, line up, okay? And if we were to do that, we would basically come up with the equation for a parabola, which you might remember from our discussion on spherical mirrors. It's easier to make a spherical mirror than a parabolic mirror, but a spherical mirror, as long as it's not too big, right, will be a good approximation to a parabolic mirror, and so we can create a couple of spheres like this. Let me just do my best job of drawing a couple of circles of the same radius. You get the idea. So its centers would be here, right? But if they're the same curve, if they have the same radius, right, then the average of these 2 points will be right here in the middle. And so what we call the center of the curvature of radius will now be in between these two. And so now what I'm going to do is construct this intersection here, like that. And then I'm going to get rid of the circles that I derived this all from, you see? And so what I now have is what we would call a, what do we call this? It's convex, so it would be a biconvex lens, I think, because there are two of them, right? It's two convex lenses back to back. If it was biconcave, it would look like this, okay? But we'll talk about, that's a divergent lens. This is a convergent lens, okay? We'll get into that in more detail later, but we'll talk about the convergence part now. So, don't forget that we've got these two spherical surfaces here, right? And so this is going to somehow act like a focusing device. It'll have two focal points, one here, one here, where this focal length distance is the same, right? So this distance would be f. I'm not going to draw it because we're going to draw some rays here in a second. But this distance would be f, and this distance would also be f, little f, right? The point would be big F and maybe big F prime, okay? So you'll notice here it says thin lens. Why thin lens? So the assumption of a thin lens, right? The reason that we do that is, do you remember the lens equation from last week? Right? We got something like 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance, right? Yeah?
Yes.
Well, if we let this be thin, meaning that the light doesn't travel through a lot of material, which means that we're basically going to neglect what goes on inside the glass, okay? We'll assume it's really thin, and so that effect is minimized, as opposed to a thick lens, which would have a lot of glass that it travels through. Then we can't ignore what happens inside, okay? But we're going to ignore what happens inside, and we can do that as long as it's a thin lens, and that will allow us to use the same thin lens equation. I'm not going to rewrite it because it would fall out exactly like it did before, except it won't be reflected in, it's not a reflection that's going on, we're actually transmitting through it. So we'll use our rules, right? Remember we have C and then we have F. I'm going to come from this side. This will be my direction of incidence, okay? So, and there will be a primary axis, right? Which goes, I guess I should fix that point up a little bit. There we go. It passes like this, okay? Or you can call it an optical axis if you want. I keep using the term optic axis because I'm used to using that term in the work that I used to do. And optic axis really pertains to crystals that have, a particular axis, X, Y, or Z, which is, where the dipole is aligned, for example. And so it's a kind of a technical term. But I think people sometimes call this the optical axis or the primary axis. So parallel rays, right? You remember will pass through the focus. And so how would we map that out? We would draw a ray which is coming in parallel to the optical axis, and then what we're going to do is we're going to bend it through to the focus, like so. Okay? Notice how I kind of ignored the interaction here, right? But what's going on here, of course, is that there is refraction taking place on this curved surface, okay? But I'm kind of ignoring the, say the second one, the second interaction when we come out, and also the effect of being inside this glass where, so my rays get closer and closer to the optical axis, will be inside the glass for longer periods of time because there's more of it. So I'm ignoring all of that, and I'm just kind of drawing the ray from this surface to this point like that, okay? Then you have, rays that pass through the center, or the curvature the radius of curvature, this point C here, which is the average of this curvature going this way and this curvature going this way, which puts it dead center on the lens, will not bend, right? So light going through those points will not bend. So if I were to start from the same point here, right? I guess I should draw my image. Start from the same point, go through the center, right? I'll need my handy dandy meter stick, which seems to have disappeared. So, oops, why does it go? Okay, and that's enough, right, to get an idea of where the image is, right? You'll notice it's inverted, okay? But if I were to take a piece of paper and hold it right here, I would see an upside down version of whatever it is I'm imaging, okay? But we can, one more ray we can draw, right? Remember that rays that go through the focus emerge parallel. I'm just trying to think, how am I going to draw that? Like this, I guess. Yeah, it comes out to be about right. Stretching it just a little bit here, but that's all right. So if I go through the focus, I'm just going to have to move where the focus is a little bit, then we come out parallel, okay? So if we pass through the focus, then we will become parallel, okay? And so those are the three rays that you can use to construct, where the image is going to form for a thin biconvex lens, okay?
All right.
And I'm going to leave it to you guys as an exercise to try to figure out what the rays will look like from a what we call a biconcave lens, right? Which would, look like this. Again, it has to be really thin, right? This will turn out to be a divergent lens, okay? Whereas this is what we call a convergent lens, right? And if you're looking for an example of such a lens, right? Any pair of, what do they call these? I think magnifying glasses or reading glasses. They call them reading glasses. Reading glasses use spherical lenses. These lenses are spherical because they will focus light to a point, right? Remember that rays that come in from infinity, right, from very, very far away, will all be parallel. They will all pass through the focus. That's why if you take these outside, right, and you see I've got a light back here, you can see the light focusing on the whiteboard from the light back behind me here. Do you see that?
Yes.
Sorry again. So it's somewhere around here. So it's it's about a meter, maybe half a meter. It might be a half a meter. These, okay. Also, you can see an image forming of the light source there at the LEDs, and that looks getting blurry. Now it's pretty focused. Now it's getting blurry again. So somewhere around here, I'd say, right? And we're getting a double image because there are two lenses, right? I can block one of the lenses and we'll just get one image. Okay? But if I take that outside, right, I can focus the sun down to a point and I can start a fire, right? You cannot do that with glasses like these because these are divergent lenses, okay? And that's because that's how we'll talk about how we correct vision in future lectures that will be coming up soon. So things to consider with this, right? I'm just telling you, this lens equation still applies, right? This focal length, this would be the object distance, right? This would be the image distance, okay, from here to here. Okay, this lens equation still works. You can think a little bit about, well, what happens if I move the object distance, if I increase the object distance, right? If I move it farther back, what's going to happen to the focal plane, right? You can think about that, and I'll put some problems in your problem set that deal with that kind of thing. And if you move closer, what's happening, right? If I move closer, what do you think is going to happen to this? Let's just think about that one real quick. If I get closer, what's going to happen to this image? Is it going to get bigger, smaller? Think about this ray going from the top of the arrow through the center of the lens, right? As this gets closer, right, what's that angle going to do? If I put the focus here, the object, say, here, right? Going through these 2 points here, we'll have see that?
Yes.
So that's moving down. We would still have a parallel ray that needs to pass through the focus, right? So what do you start seeing when you get that? That's going to kind of extend out. So this ray will look essentially the same, right? You have to pass through the focus, and I'm kind of assuming that that's where the focus is. Okay. Well, I'll let you think about it nonetheless, okay? So give it some thought.